Hello there. Let's talk about registers in assembly, more specifically x86-64 Yasm Assembly. Okay, so first off, check out this book. It's a wonderful book. The author is a genius. It's called x86-64 Assembly Language Programming with Ubuntu. It's free. Anybody can get a copy of it. Just go to the website and grab your copy. It's wonderful. It's released under a copyleft license. Author's a genius. Whenever I'm trying to remember things about CPU registers for assembly, I always go to this section. I say Callee saved. I search for Callee saved. Oh, I already had it there. Callee saved. And it ends up being section 12.8.2, register usage. So before we do that, let me just give you a little quick example so you kind of know what I'm talking about here. Hopefully everybody's seen this instruction by now. This is a move instruction in Yasm x86-64 assembly. It just moves data from one place to another. It takes two operands. So, we have like operand 1 and operand 2. Basically, operand 1 is the destination operand, so we could put destination there if we wanted to. Operand 2 is the source. We could put source there if we wanted to. That actually won't, compile or assemble, but I'm just saying that's what those positions are for. So here's an example of a register receiving the value 10. We use the move instruction, and we say we would like to move something into the RAX register. We would like to move the value 10 into the RAX register. And there you have it. There's a move instruction. Okay, so RAX is a register. Let me just say real fast that it is a 64-bit register. In our 64-bit CPUs, every single general purpose register and the float registers, they have 64 bits available for us to use. 64 bits like, ones and zeros. It's like a very, very, very big number. A long time ago, we had 32-bit registers, and so these are like, twice as mathematically robust, or whatever you want to call it. And it also allows the registers to address, the 64-bit memory addressing space, which helps us go beyond 4 gigabytes of RAM in our modern computers. Helps us go far beyond what we can even achieve right now. So we have a register called RAX, and there's a list of other registers on this page here. So basically, we have the RAX register and the RBX register and the RCX register and so forth. I have a hard time remembering all these names, so I go to this book when I forget. But otherwise, you can kind of think of like A, B, C, D, and then just surround them with R and X. R kind of for register and X for extra big, maybe. So we've got the RAX, RBX, RCX, and RDX registers, and then we have a bunch of other ones further down. I like to use these down here, R12 through R15. But first, before we do that, let me just emphasize that these are general purpose registers to be used for integers or data. You can put characters in there for strings. You can put just like, whatever data you want. Inside the machine, we use 2's complement to represent integers, so it's fine. The instructions that you will do for addition and other mathematical operations will be fine with these registers. But don't put floating point numbers in these registers, because the computer, the system, the machine, won't know how to operate on that data. The thing is, integers are stored as 2's complement. I'm going to talk about that more in another video. And floats are stored in something called IEEE 754 standard, which is just like a crazy different way of storing floating point numbers. That makes more sense for floating point numbers, but because the data is arranged differently in the machine, you can't really use normal instructions. Like you can't add two floats together with the same instruction that you would add two integers together. You would have to use special floating point registers and special floating point instructions. I'll talk about floats at the end of this video, I hope. But basically, just keep in mind, these are general purpose registers to be used for integers and data only. Okay, so what am I talking about? What are we seeing here on the side here? Why does it say return value? What is going on with Callee saved and fourth argument and third argument and so forth? So there's a standard that you're supposed to use when you program. You can get yourself into a lot of hot water or you can dramatically increase your debugging time if you don't do this. This follows a standard called the ABI, which I think is short for Application Binary Interface. But basically, I just like to say the ABI. Respect the ABI. There's a plan that people came up with that says this is how you should use these registers. Don't use them in a different way. And that way, if everybody is writing, modules, and they're all going to interact together, like I write a module, you write a module, we download a module from somewhere. If they all respect the ABI, then it's pretty much guaranteed that we can expect certain things, like our registers won't become corrupted after a function call, or that we're not going to corrupt someone else's function, or whatever, right? So you can also use this to benefit yourself, even if you're the only person who is writing your code and you're not calling on anyone else's function. Then like how are you going to remember, like, what was I using this register for? Was I supposed to save that one? Was I supposed to preserve it? How was I going to return data from that function? Was I going to use this register or the other register? It's hard to remember what you yourself even did like a month ago. So if you respect this plan, then your functions will work not only with other people's functions, but with your own functions from a month ago. The other thing too is we have system calls, right? So you have like a system call. Let's say we want to move something into REX. Maybe I want to exit the system or something. Just forget about this. This is not a system call video. Suppose I want to do a system call, right? The system call itself is also going to respect the ABI. So if you start calling other services in the system call instruction, like if you want to open a file, close a file, read a file, write a file, whatever, if you don't respect the ABI and the system call is respecting the ABI, then you might have some of your data corrupted. So it's a really, really good idea to respect the ABI. In fact, think about it this way. What if you wrote a bunch of functions for a long, long time, and then like a year later, you couldn't remember what you were doing, last year? Oh, what was the return register? And it costs you a bunch of extra time debugging. Eventually, you'll probably decide to write your own standard. Okay, from now on, I'm always going to use this register for return values, and I'm going to use this register for the first argument, and I'm going to, right? You probably come up with a plan, right? Well, that's basically the ABI. The ABI covers more than just how to use registers, but register usage is covered in the ABI. So why would you put yourself through a bunch of heartache and then eventually come up with your own plan when you could have just been following the correct plan in the first place, right? So everybody should respect the ABI. So let's see. I wanted to talk next about the return value. Okay, so let me write up a little function here. Let me just say that we have a C++ function, and we'll just say it's like void f. And we'll say it calls on G, and then we'll have another function called G, and actually maybe it's not void, maybe it actually does return a long, and G just returns the number 5 or something. Okay, hopefully you've seen some kind of a higher level language before, like C++, so that you can understand what's going on here. We're just making two functions, and one is calling the other, and the second one is just returning a value to the first one. So in assembly, the equivalent of this would be, let's make a label with the name of the function, and then a little colon, and then just put a return instruction at the end of it. Wham, you've got a function. It's not going to work very well, but you do have a function at this point. So f, I'm going to try to copy the C++ function. So it's a really good idea whenever you're writing a function in assembly, try to imagine what the prototype would be for C++ and just put it as a comment at the top. So I know how the f function is going to behave in my assembly module because I put a comment up there just kind of reminding me what the prototype is for C++. It doesn't really do anything, it just sort of runs. So that's okay. And then I'll make another function down here. I'll do the long G again in a comment, and then I'll do the actual assembly version. I'll say G colon, and then I'll return. So just by putting that comment up, I kind of can remind myself now that the G function is supposed to return some kind of a value. Maybe I'll do let's do a comment up here, how about, let's say, no, I don't want to start adding a bunch of local variables right now. Pretend that we're going to print the return value of the call to G. Somehow we're going to use cout or whatever. We're going to send it to a variable, whatever. I'm just going to try to keep the assembly as simple as possible. But anyway, the point is G returns something. So how do you return, a value in your assembly function? Well, remember that higher level languages, part of why they're so awesome is they do a lot of extra work for us under the hood, and they actually provide illusions to us that make programming easier. For example, there are no functions going on inside the actual machine. I mean, I guess from a certain point of view there are, but basically the machine is just sort of like moving data and jumping to instructions and jumping back from somewhere, and it's just sort of like jumping around and executing instructions. There's no actual function. It's like if you want to pretend that you have a function in assembly, well, there is a return instruction that will help you jump back to wherever you came from most recently. But we have to implement more, is what I'm saying. So how do we return a value in an assembly function? We just have to load up the return value register. If you look at this chart again, RAX is designated as return value. That just means we have to load RAX up with something. So for example, we wanted to return the number 5, so I'm just going to load it up with the number 5 and then return. Now we've pretty much translated a C++ function into an assembly function. I mean, that's really what's happening under the hood. When you compile your C++ program, it's just, translating all the C++ into assembly. Another thing that I should probably point out is that you should use registers as often as possible, and you should try your best not to touch memory. Of course, at some point you have to touch memory when you want to save your final result or send it off somewhere or whatever. But, imagine that you have an assembly function and you're doing lots and lots of calculations. You're performing an algorithm or something. Your program will be so much more efficient by like a factor of 100 or probably more if you don't hit system RAM. Because every time you hit system RAM, like a global variable or the stack or something, then your CPU, typically in the uncached scenario, your CPU has to go talk to the system bus on your motherboard and then, send a message to system RAM and then wait for the system RAM to figure out what it's doing and then get a response back. So when your program is executing on the CPU, you can encounter a stall, which is like your program actually stops executing for like 100 clock cycles or more. Like it's a long time, at least in the most basic case. And how do you avoid that? Just use registers only when you're doing lots of calculations. The registers are built into the CPU. They're part of the CPU's hardware. So they are lightning fast compared to system RAM or your disk or whatever. I probably say this a lot, but part of the reason you would even want to code in assembly is perhaps maybe you have a big program that does a lot of stuff, and eventually you profile the program and you realize, hey, this one part of the program is really slow because it gets called constantly and it's not super efficient. That might be a good use case for writing a hybrid program where you have multiple modules. Some of your modules are in a higher level language and some of your modules are in assembly. So you take your most important function that slows down your program, that gets called all the time, or like it has like a big loop or something, and you rewrite it to assembly so that you can have more control over how often you touch system RAM to try to make the whole thing more efficient and reduce the number of instructions and just like whatever. And you can improve the efficiency of your program. So anyway, you want to try to avoid hitting system RAM. Your registers are built into the CPU. There's 64 bits. That gives us 64 bits of address space that we can reach. Back in the day, we had 32-bit systems. That means you could only have a memory stick that was about 4 gigabytes. So now we can go much further. So yeah, that's what's going on with our registers on the CPU. Back to the return value. Okay, so we have a return value here. Goes into the RAX register. And then the next thing here is it's saying that the RBX register is something called Callee saved. So Callee saved is important. Remember we said that we have to respect the ABI, right? Like you have to respect this convention because if you don't, you're going to cost yourself debug time and your functions probably won't be interoperable with other people's functions or the system call instruction. Well, so one of the things about the ABI is some of the registers are designated as the function that is being called has to be the thing that saves the register's value so that it doesn't corrupt for the caller. Imagine this, if I had a function called f, I'm going to do like f and g here. Suppose the function f is going to move something into, let's say R12, or actually let's do RBX. Move the value 10 into RBX, and then it'll call g for some reason. Maybe g doesn't take any arguments, maybe g is just kind of doing stuff. Let's just say that in a simple case, g just moves a different value into RBX. So the thing is, when the call comes back, like after we get to this next line, let's say we're going to do something with RBX. By the time we get to this line, dude, can I get the line numbers on this? Oh yeah, I forgot. Okay. So by the time we get to line 7, the register RBX is ruined. These registers are not local variables. They're not like, tied to any scope or function call. These registers are just basically global variables that are sitting on the CPU for lightning fast performance. But that means the RBX I use inside of F is the same RBX I use inside of G. So that means if G messes up the value of RBX, then if F calls G, then F now has a bad value for RBX. This is a broken program because we did not respect the ABI. The ABI says that RBX is Callee saved, which means if I use RBX in the G, then I have to preserve the value so that by the time I return, the value is the same as it was when the call first came in. So how do we do that? We'll do that with a push pop pair. I'll probably make more videos in the future about pushing and popping, but I'm going to try to keep it simple. For now, we just say, let's push RBX onto the stack at the beginning, and then we'll pop it off the stack at the very end. This basically means we're going to take the value of RBX, we're going to send it onto the stack. So yeah, we are hitting system RAM. It's a little slower at that point. The ABI will save us a little time for the other registers. I'll try to explain that in a second. But basically, we're preserving the value here with push, and then we're popping it back off, so we're restoring it. So that means even though we ruin the value at line 14, when F does its line 7, it's going to have the correct value of RBX. It's going to have the value 10. The book, and I like to call this the prologue, just meaning this is a little section of code where we're going to set things up. We're going to start getting ready to do more instructions. And then this at the bottom is going to be called the epilogue. Like this is just like the finale. We're kind of cleaning up. We're finishing up right before we return. If you wanted to return a value from G, then you could put the move inside of RAX somewhere else. Like you could put it like below the epilogue or just above the epilogue. It's fine as long as you're sure that RAX is not getting trampled upon. So it's important to note also that if I do let's say a system call right after that, let's say I call G and then I do a system call with, some other number as the call code. I want to open a file, I want to close a file, I want to read or write a file, whatever. I want to ask the system to do something for me. The system is also going to respect the ABI, which means I'm guaranteed that RBX is not modified when the system call comes back. If the system call, if the syscall instruction didn't respect the ABI, then my RBX could be ruined. I'd have to do a bunch of stuff to preserve it. So this is very convenient. It also means that some of these registers, let me go down a little bit here, like this R10, the temporary register, and also the RDI, if you decided to use that in the body of your program, which you're allowed to, these are not designated as Callee saved, which means system call could actually ruin the value of those registers. So suppose for the sake of argument, I really decided that I needed to use, I don't know, let's just say R10, because that's marked as a temporary. I'll put a value in R10 and then I'll say, do something with R10. R10. Then that means by the time I'm done with my call to G, I should assume that R10 is ruined, because even though you can see right here that G doesn't actually do anything to R10, we should assume that we have to respect the ABI, which means the other function could have ruined it. This is especially true if you call someone else's module or system call or whatever. Same thing for the system call. So if I call system call and I use R10 at some point before and then after, then I have to assume R10 is destroyed by the time I get back from the system call. So that's no good. The cure to that, when we're talking about a temporary or something that is not designated as Callee saved, is that the caller has to save. So we definitely have to hit system RAM just to make a call. Anything that we think we need when we're finished. So I'm going to do a push. This is not the only way to do it, but I'm going to do a push R10 here, and then afterwards I'm going to do pop R10. So that sucks. And then I have to do the same thing for the system call. I can go push R10 and then pop R10. And of course, if you were clever, you probably would, put the call to G inside of that system call push pop pair, so you could have one less push pop pair. But I'm just saying there's no guarantee R10 is going to survive. So you always have to preserve it if you ever want to use it again. So this is like another way that the ABI kind of can help you save time. Notice how here in the G function, which I probably should have prototyped, let me just say, it looks like to me it's a void and it doesn't take any arguments, so I'm just going to do that. Always a great idea to prototype your functions in comments. Maybe let me do the same thing to F up here. So F looks like it's not returning anything and it's not taking anything. Okay. Whoops. Those are C++ comments that would not compile. All right, so notice how I'm using RBX, so I decide to preserve RBX, but there's also other registers that are marked as Callee saved, like R12 through 15 and RBP and whatever, but I'm not preserving those. The reason I don't have to preserve those is because I'm not using them. So the ABI can save you a little time here. Like, for example, I'm preserving R10 because I'm supposed to assume that they could be destroyed by the time the function comes back. What if instead of using R10, I used R12? So that means I don't have to surround any calls with a push-pop pair because I can trust that whoever is going to modify R12 will preserve it for me. But then notice down here, G is not actually using R12, so G doesn't even do push-pop on R12. So we save hits to memory. We don't even have to touch memory to preserve R12 because the ABI is helping us sort of stay a little bit more efficient. So this is great, right? F is a broken function at this point, though, because I'm using two registers that are Callee saved. I can't assume that whoever called F is going to know that I'm modifying RBX and R12, so I should do a prolog and an epilog up here. I'm going to say push RBX, and then I'm going to push R12. And then down here at the bottom, I'm going to do an epilog, and I'm going to pop RBX, and I'm going to pop R12. But I've done something wrong. The thing is, I'm not going to talk about the stack too much in this video, but the stack is a particular type of data structure that will return to you data in a reverse order than you sent into it. This is great for helping us keep track of function calls and return addresses, as I'll probably try to explain in this video. But basically, the data comes out backwards. So if I do it like this, then actually by the time the return statement instruction gets executed, RBX will have the value that was intended for R12, and R12 will have the value that was intended for RBX. It'll be backwards. So you have to do your push pops in the reverse order too. Notice how it's kind of like a shell that goes outwards. It's like R12 is first on the inside, and then RBX is next on the outside. That's just what you have to do to preserve everything. So the F function works now. The G function, I think it works now. We have a prolog and epilog. Okay, so we talked about the ABI, we talked about calls, we talked about the registers, talked about Callee saved, we talked about the fact that we don't have to save the other ones. I think I can talk about one thing that I should make sure to mention is that these are general purpose registers. They're to be used for integers, integer data, or like characters, or just like regular data. They use certain instructions that are not to be used with floating point data. So you actually should not store floating point numbers inside of your general purpose registers. You should only store floating points in special registers, which I'll talk about at the end of this video. So keep that in mind. Floating point numbers are stored differently in the system. They're stored with a scheme called IEEE 754 floating point. So like, the numbers wouldn't make sense. Integers and floats are stored differently. So the hardware is wired differently to operate on two different types of data. So anyway, I just want to say that this is only for integers and general purpose data. So now let's look at the other types of registers. So notice how RCX and RDX and RSI and RDI are designated as arguments, first, second, third, and fourth. Okay, so let me write like a quick C++ function here. And this is going to be, let's say we have like a function that returns some value. We'll call it f, and we'll say that f takes in some arguments. Let's say that it takes in 3 arguments. Again, we can only use integers right now because we're only using integer registers. We can't use floating point arguments or return values. Just keep that in mind. So I'm just going to do like 3 arguments, long A and B and C. Okay, so we can take in 3 arguments, and maybe we're just going to return, A plus B plus C. Okay, simple C++ function. Let's do this in assembly. We'll make a label, and we'll do a little comment that just reminds us what's the prototype of the function that we're trying to implement. We stick a little return instruction at the end of it so that it will jump back to the caller. And then we'll say, well, when the caller of this function called us and gave us A and B and C, how do we get A and B and C? Well, A is the first integer argument, so it's just going to be the RDI register. So we'll literally just use a move instruction. Let's say we want to, for whatever reason, use the R12 register, and we'll do something with it later. We'll print it, we'll save it, we'll do whatever. Let's just grab the incoming argument. So we'll just grab RDI. So I'm going to put a little comment up above here, grab A and do something with it. And I'll just write down here more instructions just to denote that we're doing something with the A value, but I'm not going to write it down here because I don't want this to get huge. So we'll do the same thing with the B. Maybe I should remember that programming is case sensitive. We'll do something with the B. It's not RDI, it's the second argument, so that's actually RSI. And then we'll do something else. We could have used R13 or other registers if we wanted to. I'm just showing you how to grab incoming arguments. So then we'll grab the C and do something with it also. It's not going to be RDI, it's going to be RDX. And you can do this up to like, I think, 6 arguments. Let me just double check here. Yeah, so like R9 ends up being the 6th argument. And if you want more than that, then the caller will have to put stuff on the stack. And in fact, if you kind of like understand what's happening here, let me just do like a main function, pretend that there are arguments there. If f, let's say we do C out whatever f returns, this is like a typical function call, right? So we'll call f. F will jump in there, it'll jump into its body, it'll do some sort of a manipulation with the incoming arguments, it'll return a final value, then that final value gets printed out. So what's 5 plus 6 plus 7? That's 11 plus 7, so what is that, like 18? I'm bad at math, so let's just say that's 18 gets printed. So what happens is, we return, oh, I forgot to return. I'm going to say compute the sum of the things, and I'll just say like blah because I don't want to put a bunch of addition instructions here, and we'll just like store in R13, let's say. So then when we have finally computed our result, I'll just move R13 into the return value. And what I'm really trying to say here is, if you imagine a function that behaves this way in C++, then what I've written down below is really what's actually happening in assembly. Your compiler compiles the code down to assembly language first, and then it assembles it down to machine code. So really, this is what's happening under the hood. It's not like a special trick. When you call a function in C++, literally, the A, B, and C have been loaded up just before the jump instruction to go to that, line 9. They've been loaded up with the appropriate values. So that's part of like, the magic of what higher level languages give us. It just makes things a little bit easier. Okay, so I've written a bad function. Notice how I'm using R12 and also R13. If I had only used RDI and RSI and RDX, those are not designated as Callee saved, so I wouldn't have had to preserve those. But because I chose to use R12 and R13, I have to preserve those for the caller, even if the caller's not going to use them. So I'm going to do push R12 and I'm going to do push R13, and then at the bottom, let me do like a prologue here. The comment prologue is kind of helpful because it kind of helps you remember, like, oh, did I forget the prologue? Did I forget the epilogue? They got to match. And then I guess the fact that you can see the words prologue and epilogue also helps remind you that everything is supposed to be in reverse order in the epilogue. So again, notice how R13 is on the inside and R12 is on the outside of the push pop pair. So now my program is good. And we've successfully translated a nice function call there. And we've done a bunch of nonsense in the middle that I'm not writing down at this point. We are respecting the ABI, so if somebody else uses our function in their module, then they can be pretty confident that we're not going to ruin their registers and so forth. We talked about the return value. We talked about that these general purpose registers are not for floats. We talked about pushes and pops. We've talked about function arguments, which right now we can only do integer arguments and return values. We've talked about we talked about the stack a little bit. So let me just point out that suppose you have a function. I just want to mention this briefly. Suppose you have a function f. Let's say it's void, so it doesn't return anything, and it has an integer a equals 5. Oh, I think the reason that I wanted to do this is to show you how dangerous it is to mess with the wrong register, like the stack register. So suppose we have two variables, and then we'll do something with A and B. So now suppose we have two threads. We have an execution thread 1 and an execution thread 2. If you're not familiar with threads, that just basically means your computer is literally executing your function, or sorry, it's executing twice at the exact same time. Maybe not the exact same time if you only have a single core on your CPU, but you could imagine that that's possible, especially if you have many cores. That's an operating systems video. But basically, pretend that we have an execution thread, so it's like going through your program, executing one instruction at a time. Then you launch another execution thread that also executes your program one instruction at a time. So at some point, it's possible that thread 1 and thread 2 could be executing F at the exact same time, right? So I'm not going to talk too much about this because this is not an OS video, but basically this could create a race condition where thread 1 and thread 2 kind of step on each other's toes and they both try to modify the value of A at the wrong time, and then like they get the wrong value back because the other thread modified it. So this is why local variables in a function actually live on the stack. A and B are not global variables. They're actually temporary local variables that are sitting on the stack, and the way the stack works, I'm not going to talk about it too much in this video, is that well, every function kind of has its own area of the stack. So when the function comes in, on the stack sits the return address so that the function knows where to jump back to when it returns, and any local variable that the function makes. So if you think about it, when thread 1 calls F, we actually end up with a different version of A and a different version of B. We could imagine them as being, A sub 1 and B sub 1. But when thread 2 comes in and creates those local variables, we can imagine that we get two different versions of A and B also. So this is how the computer prevents multiple threads from stepping on each other's toes if you're using local variables. Local variables are just local to the function. This also helps if a function calls itself a bunch of times. Maybe one call or another might want to see a different version of A or B, and it would be just incredibly difficult to keep track of that if you were using globals. But when you use locals, well, they're just basically different variables altogether. So what I'm trying to lead up to is the stack is pretty important. If you corrupt the stack, then you probably are going to crash the entire program. You might make it so that a function doesn't know where to return from. Like when you do the return statement, it might jump to some other part of the code that doesn't even make sense, and then everything crashes. Or you might mess up some data in a local variable. Like if you mess up the stack, you might be messing up the local variable that the caller is depending on, and so then the caller continues to execute and it sees the wrong value and it just crashes. Or you might even mess up your own local variables. So don't mess with the stack. The reason I'm saying that now is because this register right here, the RBP, sorry, that's not it, the RSP register, that's the stack pointer. Eventually, you can learn how to manipulate the stack pointer in order to create your own local variables. That's okay once you know what you're doing. But unless you know exactly what you're doing, you probably shouldn't touch the stack pointer. Especially, you shouldn't mess with it right before you call a function or right before you return from your own function. Be very careful with that. The RBP register is similarly dangerous. It won't like automatically destroy your program, but it is it's usually, I mean, it's quite often used as sort of like a bookmark for where the stack pointer was pointing in other modules and other functions. So if you fail to preserve the base pointer, the RBP, and then you return from your function, then you might have actually messed up the stack pointer for the caller or some other caller somewhere in like the ancestry of your call graph. So be very careful. I mean, I guess all Callee preserved variables or registers you should be very careful about, but these are like kind of the two worst ones to forget about. There's also another register that is not listed on this page called the instruction pointer. It's RIP. It basically is a register that holds the memory location of the next instruction to be executed. So if you modify that, then you just told your program to go execute in some random crazy place, and probably everything is going to crash. R10 and R11, I can't remember already if I explained this, but I'll just say it again. R10 and R11 are just temporary registers. You don't have to preserve them, but the callee, if you call another function, they don't have to preserve the registers either, which means it can be really fast to use R10 and R12 if you're kind of like already running out of registers. If you don't have to make a function call anywhere, so you know no one is going to ruin your R10 and R11, then you can also use R10 and R11 to sort of like, you know, reduce your hits to system RAM to speed up your program. So R10 and R11, they should probably be used last. R12, 13, 14, 15, I usually use those first. Once I start running out of those, Callee saved, then I'll start eating into the arguments. I'll say, you know, I'm going to start using RBX, and then I'm going to use RDI and RSI and whatever. It's okay if you use, you know, the argument registers, as long as you've already done something with your incoming arguments or you don't have any. So just keep that in mind. You're allowed to use them. I mean, this is all just a standard. As long as you obey what the rule is, then you'll be all right. The rule is you got to Callee save those. The rule is that one's just temporary. The rule is this one's an argument, and so forth. Okay, so I think I've mentioned a lot of stuff about locals and how we use these registers. Let me try to just show you one more thing real fast. So I said before that the size of the REX register is 64 bits because it takes up the whole available register bits in the CPU, but there are other versions of this register that we could use. What if you only wanted to use 32 bits in your register? Or what if you wanted to pack like two different 32-bit numbers in the same 64-bit register? You could do that. There are also older modules and instructions that will operate only on 32 bits. So how do you reference only 32 bits of a register? Well, if I search for, oh shoot, what was it? Is it EDI? No. Shoot. It's in here somewhere. This is like a good lesson in actually preparing before you record a video. So I'm going to do architecture overview, CPU registers. Oh, it was at the beginning of this section. I always skip down to 2 point or 12 point something, and I should have gone to 2.3.1.1. Okay, so obviously I'm not going to remember all of this, but basically, notice at the top, we have the REX register. all 64 bits of it. But if you wanted to access the lowest the lowest 32 bits, then in your code, instead of putting RAX, you put EAX. So for example, move RAX, RAX, let's say the number 5, but over here we're going to move EAX, the number 5. Here, it's going to set the whole 64 bits to just like a bunch of zeros, and then there's going to be a few bits that help represent 5, the lowest bits. So it's going to erase like the whole thing, all 64 bits. But if you use the EAX instruction, then only the lowest 32 bits will actually be modified, which means whatever data you had in the higher 32 bits of the register itself, they're just going to stay there. It's going to be considered junk data at that point. So sometimes, if you're going to work with something that's going to be using only 32 bits of your register, you better make sure that the other bits are cleared out if you intend to use RAX right after that, and vice versa. So keep in mind that we have other forms of the same register designation, but just to let the CPU know that we only want to touch 32 bits worth, we only want to touch 16 bits worth, or 8 bits. And this kind of table covers all of the registers, RAX, RBX, RCX, and so forth. I think it doesn't cover the instruction pointer and something else in there, but most of them. However, for my purposes, I usually just use 64 bits because I'm not like super advanced, unless I have to divide or do something. Okay, so that's the last thing I wanted to mention about the general purpose registers. Let's see. Callee saved. So not sure if I said this before already, but basically so just to emphasize, the RBP register is the base pointer register. You're probably going to mess up the caller, because the caller often uses RBP as a bookmark for the stack pointer. You definitely don't want to mess with the stack pointer unless you actually know what you're doing in order to create local variables. There's another register in here called RIP, which is the instruction pointer register. So if you mess that one up, then the program's going to start executing in some crazy place that doesn't even make sense. Okay, so now that we've talked about general purpose registers, by the way, I should have mentioned before that RBP and RSP, they're typically called special purpose registers, not general purpose. General purpose is like RAX, RBX, all these ones that you can just randomly use as long as you respect the ABI. But the base pointer and the stack pointer, those are kind of special. And the RIP, the instruction pointer, that's a special register. You shouldn't mess with those unless you really know what you're doing, or you'll get yourself in trouble. But now that we've talked about those, let's talk about the floating point registers just real fast. I'm not going to talk too much about using floats until a lot later, but basically, I at least want to mention that we do have registers that will work with floating point operations. Let me see. There we go. Okay, so it's 18.2 floating point registers. Essentially, we use XMM0 through XMM13 for floating point numbers. There's not going to be any crazy letters like RDI, RSI that you have to memorize. You can just use 0 through 15 and it's totally fine. When you want to return a floating point number from a function, you will load up XMM0 as the return value. You won't even touch RAX. The arguments are the same. They're just kind of ordered. It's like the first argument is going to be XMM0, the second argument is going to be XMM1, and so forth, all the way up to XMM15. If you need more than 15 arguments, you're going to have to do some sorcery with the stack, or with some kind of system like the global variable or something. And also for floating point registers, we use different instructions. So what I really want you to know, because this is mostly about the regular registers, is that if you have floating point numbers and you want to multiply them or do some other operation on them, the normal instructions for regular registers won't actually work. You'll have to look up a different set of instructions. For example, and I'm going to do this in another video some other time, if you want to move data with a floating point register, you can't just use the regular move instruction. You got to use either move SS or move SD. And both operands have to be floats. Or actually, I think the one on the right can be memory. But Move SS basically means single piece of data, single precision. SD means single piece of data, double precision. So you can move like multiple pieces of data at a time. I'm not going to really cover that. But you can move single precision floating points, which means they're 32-bit floating points, or you can move double precision floating points, which means they're a full 64-bit floating point number. There's also bigger registers, but I'm not going to talk about that. Yeah. Well, yeah, later processors 256. I think mine has that, but I'm not going to talk about that. I think mine are like YMM or something. So yeah, with that, those are the basics of registers and some stuff to keep in mind. In future videos, I'm going to talk more in depth about making functions and calling functions and all that stuff respecting the ABI. But for now, here is your primer. I hope it was useful on CPU registers. Thank you for watching this video. I'll see you in the future. I hope you had a little bit of fun and you learned a little bit of stuff. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.